previously seen that adding a non-volatile solute to a solvent changes the vapor pressure of the solvent and therefore its boiling point. Now, different classes of substances produce different effects on the boiling point change. Those substances which are known as non-electrolytes all behave in about the same fashion to produce one kind of effect on the boiling point. Other classes of substances, those known as acids, bases, and salts, which we have previously studied, produce abnormally great effects on the boiling point of the solvent. And we wish to illustrate both of these effects today. We are now examining a sample of pure distilled water which is boiling in the test tube. We have inserted a thermometer above our boiling distilled water, and you will observe that the distilled water is boiling at 100 degrees centigrade on this thermometer. We will now obtain the boiling point of a solution of urea, which is a solute that behaves normally. This solution has a concentration of 2 molal, which means that it contains 2 molecular weights of urea dissolved in 1,000 grams of water. I'll add a few milliliters of urea to the test tube. Then place the burner under the tube, cause the solution to boil, and we will then determine its boiling point. You can see that the urea solution boils at about 103 degrees centigrade. Next, we will determine the boiling point of a 2 molal solution of sodium chloride in water. This solution is made up in such a way that 2 formula weights of sodium chloride are dissolved in each 1,000 grams of water. We'll now place the burner under this solution and observe its boiling point. The sodium chloride solution boils at about 105 degrees centigrade. So the elevation caused by the presence of the sodium chloride solute is not quite twice as much as that caused by the urea, but is substantially greater than that caused by the urea. In your previous study of solutions, you saw that the vapor pressure of the solution, and therefore also its boiling point, was changed by the presence of a non-volatile solute, and that the only important factor to be considered is the number of solute particles present in a given number of solvent particles. Now, we've just compared the boiling points of 2 solutions, urea and salt, of equal molality. This means that we've taken 2 formula weights of urea and 2 formula weights of sodium chloride and added them to, in each case, 1,000 grams of water. Now, the urea solution had a higher boiling point than pure water. The presence of the non-volatile urea then did raise its boiling point, and it did so because a certain number of urea particles were present. In the case of sodium chloride solutions, however, the boiling point was raised to a higher temperature than that of the urea, even though we had 2 formula weights of each solute present. And the explanation for this is that in the sodium chloride solution, the formula weight of sodium chloride in solution was dissociated into a sodium ion and a chloride ion. And therefore we have in the salt solution approximately twice as many particles as we do in the urea solution. And this additional number of particles caused the higher elevation of the boiling point in this solution. The apparatus which you see has been adapted to show us the roughly at least, the conductivity of several different solutions. The calibrations on the instrument on the right have no actual physical meaning and simply will indicate the extent to which the solution being tested conducts the electric current. These two small copper wires are connected to a source of direct current. And we see that essentially no current is flowing between the two copper electrodes. Next, we'll test the conductivity of a urea solution, similar to the one that we used in the boiling point experiment. And again, we observe no conductivity. Next, we'll test a dilute solution of acetic acid. And we get a reading on our scale of between 2.5 and 3 units. And finally, we'll test the conductivity of a sodium chloride solution. Again, similar to the one we used in the boiling point experiment. And this time we obtain a reading of about 4.5 units. From this experiment, then, we see that the solute which has the highest conductivity, the sodium chloride, is also the solute which produced the most abnormal effect on the boiling point. Our conductivity experiment showed that pure water gave no conductance that we could measure with our instrument, and neither did urea solution. This, of course, is because electrical conductance depends upon the presence of charged particles or ions, and these solutions contain very small concentrations of charged particles. With acetic acid, we measured rather low conductivity. This is true because while acetic acid and water react to form hydronium ions and acetate ions, the number of these ions present at equilibrium is very small compared to the number of unionized acetic acid molecules. So the small number of ions produces a low conductivity. In the case of salt solutions or sodium chloride solutions, all of the sodium and chlorine is present in the form of charged particles. The concentration of these ions is high, and the solution is, therefore, a good conductor. The conductivity of a solution depends not only on the solute, but on the solvent as well. In this small beaker, we placed a few milliliters of a solution of phosphoric acid in alcohol. And you'll notice that the solution conducts the current to a small degree. Now, to this alcohol solution of phosphoric acid, we'll add a few milliliters of distilled water, which is itself, as we saw earlier, a non-conductor. And you'll observe that the addition of the non-conducting distilled water to the solution of phosphoric acid and alcohol has resulted in a mixture which conducts the current very well. In fact, the original conductivity of this solution was probably due to traces of moisture which dissolved in the alcohol from the air in the room. First, we wish to examine the conductivity of solutions of two acids, acetic acid and hydrochloric acid, and then see how the differences in conductivity have implications in other sorts of chemical reactions. In this beaker, we have a solution of acetic acid, about 6 normal. And you can see that it has some conductivity, but not very much. We'll then replace this with a solution of 6 normal hydrochloric acid. You see the conductivity is substantially greater. Now we'll compare the rates of reaction of these two acids with zinc. We saw previously that solutions of hydrochloric acid in water were much better conductors than were solutions of acetic acid. Now when acids react with active metals, such as zinc, the reaction is actually between the hydrogen ion and the zinc. And therefore, solutions which are more highly ionized should have a higher concentration of hydrogen ion in their solutions. This means that hydrochloric acid should react with zinc more rapidly than acetic acid. And we can test this prediction by experiment. In the two test tubes, we've placed small quantities of mossy zinc. And to the tube on the left, I'll add a few milliliters of dilute acetic acid. To the other tube, I'll add an approximately equal amount of dilute hydrochloric acid. And you can see a very definite difference in the rate of reaction. This illustrates a rather general property. Because other things being equal, ionized solutes will ordinarily react more rapidly than molecular solutes. And we see an example of this phenomena in the reaction of these two acids, acetic acid and hydrochloric acid, with zinc. The ionized acid reacting rapidly, and the weakly ionized acid reacting very slowly. When we tested the conductivity of phosphoric acid in alcohol, we found that the solution was not a very good conductor. But then when we added water, which is also not a good conductor, we found that the mixture then conducted very nicely. The explanation of this is that the water molecules interact with the phosphoric acid molecules, forming hydronium ions and dihydrogen phosphate ions. And these ions, which were not present before, are the cause of the conductivity in the mixture of water and alcohol and phosphoric acid. Then we tested solutions of two different acids with zinc. We found that when a low concentration of hydronium ions was present from acetic acid, that the reaction was very slow and small amounts of hydrogen were evolved. However, when we used large amounts of hydronium ion, these can be obtained from any strong acid. In this case, we used hydrogen chloride. We found that this high concentration of hydronium ions from the hydrogen chloride resulted in a rapid reaction and the rapid production of hydrogen. So the rate of evolution of hydrogen, then, when active metals such as zinc react with acids, depends primarily on the concentration of the hydronium ion in the solution. When an electric current is passed through a salt solution, the ions in the solution actually migrate or travel to the respective poles, the positive ions moving toward the negative pole and the negative ions moving toward the positive pole. In the experiments that you've seen up to this time, however, all of the ions involved have been colorless, and this migration was not observed. This experiment actually demonstrates the migration of ions during electrolysis. In order to demonstrate this phenomena, we've used colored ions. The bottom of this U-tube contains a mixture of blue copper ions and yellow or orange dichromate ions, yellow in the concentration we're using, and the mixture appears green. These two ions, solutions of these ions, have been mixed with agar, a material which sets up much like jelly. This is to keep the ions from diffusing too rapidly. Above the agar copper dichromate mixture, we've placed on each side a layer of clear agar. And above the clear agar, a solution of dilute sulfuric acid and a solution of potassium nitrate. Now this apparatus will be connected to an electrolysis setup. Two electrodes will be inserted into the solution. These will be attached to a source of direct current. And as the electric current is passed through the solution, you can see the blue copper ions migrating toward the cathode and the yellow dichromate ions migrating toward the anode. Now this migration takes about 45 minutes. And in order to speed up the sequence, we've used the technique of time-lapse photography, so that what you will see in about the next 8 or 10 seconds actually took about 45 minutes. In this film, we've seen the effect of different types of solutes on the boiling point of water. We've examined the electrical conductivity or lack of conductivity solutions of several different materials, and these results were correlated with their effect on the boiling point of water. Then, we also saw how, during electrolysis, the actual migration of ions can be demonstrated.